Welcome to the Lean Learning Seminar. It's a pleasure to introduce this week's speaker, who is Michael Douglas from Harvard CMSA, and he will be speaking on formalizing the axioms of quantum field theory. Welcome.
Thanks. Let me share my screen here. Is this good? Everybody see the screen? I'm going to assume it's good. I see it. Okay, so I'm going to talk today about formalizing quantum field theory. This is a joint work with Sarah Hoback, who's a grad student in Harvard physics. And I won't tell you a lot about quantum field theory. I'm going to focus more on the theorem proving and formalization aspects, as many of these talks do. But certainly, whatever you have questions about, please ask me. And the talk will have two parts. I'll give some overview, which I'm sure will have overlap with many other speakers. And then I'll give some demonstration of the coding assistance technology that we've been using to do this. Okay, so the idea that you could formalize the term didn't exist until maybe this century or the 20th century, but the idea that logical argument could be reduced to almost a mechanical procedure is ancient and has taken, well, yeah, it's relative. It was part of the development of rigorous mathematics. So mathematical logic has a very central foundational role, and of course, many mathematicians around the 1900s asked these questions. Hilbert asked very clearly, can one base all of mathematics on some complete set of axioms and prove that they're consistent? And famously, Gödel showed, well, no, you can't prove that they're consistent, but you can effectively, as it turns out, express, so far as we know, all of mathematics in a formal language. And maybe that one needs to extend the language to make new statements, but one can still do it in this formal way. And then that's, in a sense, the foundational definition, if you will, of computer science, that a machine can do processes that we would regard as reasoning and that can establish proof. So in a systematic treatment, one would, I think, go through various forms of logic from the simpler to the more sophisticated. The more sophisticated really is pretty complicated to understand the foundation, so you don't need it in depth to use Lean. So propositional logic, of course, everybody learns this in school. And there's the idea of a proof procedure. So there is this, check that a collection of statements is a tautology or satisfiable, has some satisfying assignment of true and false, or is true for all those assignments. But those in general are hard computationally. You really just have to, in general, try all the possibilities. Now, once you've found a satisfying assignment, it's very easy to check that your propositional statement is satisfied, and that's this statement, this conjecture that everybody believes that P is not NP. So it can be much easier to verify a proof than to find a proof. So that's foundational to computer science. And then for proving that a set of statements is a tautology, always true, it's often the case that you do it by not enumerating all the possible truth values, but by using rules of inference, these rules of deduction that I've quoted, such as modus potens. And so that's a proof system. So that's the starting point. And again, from a computer science point of view, there's a lot to learn even from that starting point. But of course, to express mathematics, you need much more. The basic distinctions are you can have variables that can take values in sets, and that quantifiers, that's first order logic. You can quantify over functions. You can replace sets with type theory, which is what we'll use. But the basic structure of the problem is the same. All these logics, there are many logics that can be efficiently verified and in which you can express, again, quote, all of mathematics, but there's no easy way to find a proof or disproof. And so that's what gives rise to this idea of an interactive theorem prover that given that there's not an efficient algorithm to do it, will help the user to try to do it, to employ efficient algorithms for those parts of the problem for which they exist, and then to strategize and put the pieces together to get a proof. So here's this lean language. I'll go into much more detail about my example later, but I'm sure all of you have looked at it. And again, I think the basic statement here is that the statement here that there are infinitely many primes is quite intuitive and close to standard mathematical language, but the proof is understandable, but not that close to the way you would write it in human mathematical language. Okay, so there's another perspective on this computer science point of view, which discusses the lean as a language. Okay, and then from that point of view, there are comparisons and similarities and differences with programming languages. And so the biggest difference between, say, Python or C and many other languages, also including lean, is that C and Python are procedural languages where you can write things like x equals x plus 1. And of course, that's nonsense as an equation that just has no solution in the finite numbers. But it's a meaningful statement because what it says is to assign the variable x to its new value, its previous value plus 1. And so you think of x as this little box holding a number. And that's a very good model of the computer hardware, but of course it's very far from the way that we think about mathematics. So if this was your ingredients, you would have a very hard time expressing any mathematics. Now, one step towards mathematics is to not do that and instead just define functions. And of course, there's a great deal that you can easily say and naturally say in terms of composition of functions. You can map a function over a list, sort you can regard as a function, or again, that's very mathematical. And that was a step that was taken in programming languages independently of this theorem proving trend. And there are many functional programming languages, but of course that's just a start because we need to talk about for all x quantification, there exists an x. We need to talk about proof by contradiction and so forth. And so it was a lot of work, and this was, I don't know, a multi-decade process to try to reformulate all these concepts in ways that are more like programming languages. But the system that's used in Lean was not totally, but largely worked out in the 70s and the development of the language Coq. And I'll, again, review a bit of it from this kind of perspective. And so here's first order logic. Again, it really does actually express more of mathematics than you might think. So it depends on what sets you allow. But if you allow, say, the natural numbers, the integers, you can express Fermat's theorem. There's even a restatement of the Riemann hypothesis in these terms. But the main lack of first order logic is that you can't quantify over functions. A variable cannot denote a set or a function. You cannot, and that's very limited. You can't naturally express real numbers, for example. You can express them in terms of axioms, but of course they have other models than the standard real numbers. So that leads you to a higher order logic so that you can quantify over these larger sets. And then this very, if you're not naive about this, this leads very quickly to paradoxes, this sort of, Russell paradox and so forth. So this was, again, 100 years ago. And 100 years ago, people, Russell, in fact, introduced this type theory where you can't talk about general sets or sets satisfying simple conditions. You have to give some sort of explicit rules for constructing the sets. And that's, in a sense, I mean, type theory is not literally that. You should not think of it literally as sets, but it's much like saying whenever we use a set, we give some rule for how the set is constructed. So for example, the natural numbers, we could say 0 is a natural number, and we have a successor operation that defines a successor of every natural number. And then the universal model of this that makes no more assumptions is, of course, the natural numbers. And so that's natural number defined as a type. And so all the modern theorem provers are based on types, but not all are based on what's called a dependent type theory. And to make a long story short here, a dependent type is a language where you can express new types constructed in pretty general ways from the old types. And the basic example would be to say, suppose you want to define a matrix over some field. Well, it would be very natural to say, I have the field, I have the the rank of the matrix and so forth, where I can specify an explicit index set. And then the matrix type is a function of those two, a type and an index set. And that's a quite sophisticated thing to make work in generality. If you try to do it in full generality, you find that your rules for deciding when types are equivalent turn out to be undecidable. So you want to avoid that. You want something which is general enough to define all the types you would naturally use in mathematics, but not so general that the problems of working with the types become computationally difficult or even undecidable. So all this is the background that led to developing through the development of Coq, and then Lean is basically a modernization of the lessons learned from Coq. Okay, so now we have Lean 4. We have a sizable community using it. I should update this slide because the Lean Math Lib is almost 2 million lines of code now. So it's a lot of the undergraduate math curriculum. It has many more advanced results. The measure theory is going to be very crucial for what we describe later. You've probably heard in other talks some of these recent accomplishments that people have formalized various famous theorems. The liquid mathematics experiment, very famous verification. Here's a few examples. Again, I don't think I need to go through it for this audience, but just to give a flavor of simple statements in Lean. And again, to come back to these foundational and quite interesting, not that you have to know it, but there is this sense in which there's a direct correspondence between logical constructs and programming language constructs. And so you can think of proofs as instances of proof types. So once you have this fully general dependent type theory, then a lot of logical concepts get subsumed into that. And so, for example, just to give one, if you want to prove P and Q, well, clearly, if you have a pair of a proof of P and a proof of Q, then those together should give you a proof of P and Q. And so you can make that the definition of the AND operation if you are working within this framework. A proof of P and Q is exactly this pair object where the components are the separate proofs. And there's lots of things. The implication is one where, in fact, it's just in a way even more natural than implication. If you have a function that takes a proof of P and returns as output a proof of Q, well, then you've proven P implies Q in a very constructive way. Not only is it true logically, it's true that you have a way of making the proof automatically. So, again, this becomes interesting, especially if you try to connect this to programming languages, which we won't do in this talk, but is an important ability of Lean. So there's an in-between step of talking, using constructive logic, where everything you construct, can be explicitly constructed. You're not allowed to use excluded middle, but you could still, in principle, be using inefficient algorithms, things that could be computed in principle, but not in practice. Okay, here's coming back to this proof of the infinite primes, and making now a little bit more detailed point that we have this tactic style proof with let a variable be something. We have various intermediate propositions, and we call upon these various tactics to rearrange the statements, the substatements, and the goal. And again, it takes some learning to write this code. And what I started saying really a couple of years ago in my talks is that Lean is like the assembly language of proof. And that analogy, if you know computer assembly language, especially from the old days, is, well, first of all, assembly language is very clear and from the computer, very easy to execute, but very hard to use. And similarly, Lean in practice is very much designed to be relatively efficient to verify. There are no tactics, or there are tactics that actually do searches where you can't bound the amount of time it takes to do it, are discouraged in Lean and generally not used. But once you have figured out how to write it in this form, the proof can be very efficiently verified, and again can really express these quantifiers, functions, all these attributes of very general mathematics. So here's the standard type of goal, proof goal structure that you get in the assistance. This is something that we use in the proof that I'm, the formalization I'm about to describe. So there is, again, not a lot, but the basics of a Fourier analysis are there in Lean Math Lib. And again, the list from the documentation. Okay, so I want to give a little advertisement. This is kind of a digression, but there are various areas of AI and math that we talk about. We had a big program in this a year ago. We have many talks in my seminar series at the CMSA, and although interactive theorem proving is very important, there are many others that are in fact not even machine learning or AI in the first instance. You can always try to use AI to make something faster, but some that people should also know about because they are advancing rapidly are verified computations, what you could call verified mathematics, where it's in a way simpler than theorem proving. It is something where you could write a program and do a calculation, but you can say, can my computer calculation, let's just say, add a list of numbers, produce a rigorous result that I could actually use in a mathematical theorem? And of course, naively, the answer is that's, well, sure, 1 + 1 + 2, that's both a numerical calculation and a totally rigorous statement. But people generally, at first would say that the answer is no, because once I start working with floating point numbers, I'm going to add floating point numbers, and I'm not going to be able to express the result with the same accuracy. So I'll need to round off. And what does rounding off do? Well, it's this kind of engineering thing. What do we say? And on the other hand, there are relatively simple ways to solve it. And in the case of adding numbers, a simple thing you could say is let's always round the result up. Okay, so that's a consistent rule. That's something that the computer can implement. And then I interpret the result not as the exact sum. I interpret it as a rigorous upper bound on the true sum. And that can be made rigorous. Certainly the concept is very clear, and it is true if you think about it, that can be a rigorous interpretation of a computation. So if you're very careful with the way you do the computations, they can be used as ingredients in rigorous proofs. And then this very much broadens the scope of these techniques because, of course, there are lots of problems where there's no simple analytic solution, maybe no, non-constructive proof, So famous example where, there is a proof which is semi-constructive, but very, very difficult, of course, is the famous Xing-Tong-Yao theorem of the existence of a Ritchie flat metric on a Euler manifold of zero first Chern class. And again, this could be the topic of a whole talk in itself, but this is within the range of these verified numerical techniques to reprove examples of this theorem, basically to take a numerical approximate metric and try to use a fixed point theorem to show that, yes, nearby there really is an exact Ritchie flat Euler metric, and then we're going to compute the estimate. So in Yao's proof, that's what he did, and he had these very difficult a priori estimates. But in principle, you could take the approximate numerical solution and compute upper rigorous bounds on the same estimates that you need to make this argument work. And that would be a reproof of the theorem, which wouldn't be as beautiful or sophisticated as Yao, but could be automated in that sense much more general. You could apply the same tactic to many problems. So that's a thing worth knowing about. And of course, there are many other calculations which it's much easier to say what is a rigorous proof of a calculation. Let's take, you have some, problems in algebra, you have problems in group theory, which can be reduced to algebra. So algebra, you have to take limits, there's axioms, what an argument is. It's just that, again, lean is optimized for proving any theorem in any part of mathematics, which is not necessarily, you need special tools to prove complex algebraic results. And of course, there are other packages for doing that. Many, there's in math, Magma and Gap and such. And so ideally, one would have something where the powerful system would prove these complicated algebraic statements with algebraic proofs and then translate the proofs, say, into lean, something that can be verified. And there's been work on that too. That's an example of this verified mathematics. Okay, so to continue this kind of survey of state-of-the-art techniques, of course, the analogy with the assembly language suggests that maybe the computer should be writing this lean code, and the humans. It's good that the humans look at it, and kind of correct the computer. But just as compilers were a big step forward, and you rarely have to look at assembly language because the compiler translates a higher level language into the assembly language. You might try to make the same claim for lean, that there should be some higher level math language that requires fewer statements. Maybe it's still lean, but just with much sketchier arguments, or maybe it's some higher level language that's allowed to have like search steps and these things which are not necessarily efficient. And this kind of technology has been around for a while, not using classic, machine learning or AI. There's this idea of the sledgehammer, which was first developed for Isabelle, where you select, if you know the library results, you need to prove something, and you combine all of the higher order results together, there is a way of translating it into first order logic that then first order logics are much easier. It's not like there's an efficient algorithm for proving it, but it's much more efficient than the higher order logic. And then often, although there's not an algorithm translated back to lean, this gives you a great deal of information once you found this proof. So this technology has existed for something like 15 years. There's been a project at the Hoskinson Center at CMU to develop a hammer for lean. Now, you might, of course, say that's very good, but it has special purpose. Why don't we just turn AI loose on this problem of trying to automate ITP? And again, this has been successful in the sense that it's been a research topic which has been advancing for several years, kind of the late 2010s after the machine learning, and especially after AlphaZero came along, that could play Go against itself and generate arbitrary amounts of training data and therefore have no a priori limit on its performance, and indeed rapidly became superhuman. And so you might try to say the same thing about math. Math is this unbounded source of provable statements. And if you can generate more and more valuable proven statements, you could have an analogy to AlphaZero, a system that got better and better at math. And many people are chasing this kind of dream. And so the early approaches used a very direct analogy to AlphaZero and reinforcement learning. And then, of course, language models came and started to be able to do this about just 2 or 3 years ago. They started to have this ability. Now, last year, the state of the art was systems from Google DeepMind, Alpha Geometry, and Alpha Proof. And here's the Alpha Geometry, which again, a year ago was pretty impressive. But now, of course, several groups have been able to get gold medals at the last IMO in July. And in fact, a different group within Google and another group at OpenAI was able to basically get standard language models to get gold medals. It's not exactly the one that you get by paying and going on the web, but it's not that different. It's just fine-tuned on more math. And so both approaches are being used now. And in fact, there's more of a debate now than there was, say, a year ago. Do the language models, do AI need formal verification of something like lean to work with mathematics, or could it be that they'll be smart enough to only maybe not use lean or formal math, or maybe use it the way humans do, that once you've found the proof using other reasoning, other methods, then you translate it to make sure that it's sure that it is correct. So again, this is very active field right now. There's a program that recently started at DARPA, and a solicitation for grants that they want to make formalization much faster. And their target is this idea of auto-formalization that Christian Szegedy was one of the originators of, that if you could translate just ordinary math that people write, maybe papers on the archive and journals and so forth, into formal math, well, that would just solve the problem once and for all. We just translate the whole math knowledge base into formal math. And DARPA's explicit goal is they believe that formalization over pure human efforts will be sped up by a factor of 103 years. And in fact, this may be less ambitious than it seems, because a great speed up has actually been accomplished just this summer, just in recent months. A company called Math Inc. that many of you will have heard of has a system that can do auto formalization, or perhaps 10 or 20 times faster than doing it by hand. To take Jared Lichtman's, we had a talk about this at Harvard recently, and Ben and others of you are working, in fact, on trying to do this auto formalization for geometric analysis in the Ritchie flow. Okay, so that gets us into the project that I intend to describe. Are there questions about this general topic, or should I just move on to the project? I'm not hearing. I hope I hope everybody's there.
So we were good. Thank you.
Okay, good. Okay. Okay, so I'm a physicist by training. I've done enough mathematical physics to maybe be an honorary mathematician, but certainly the problems closest to my heart are physics problems, and so now it's natural for the theoretical physicist to ask, so how can we share in all this fun? Can we formalize some physics? And there's some problems with doing that. And the deepest problem, of course, is that a fair number of the interesting statements and cutting edge statements in theoretical physics are not rigorously proven. That is not the standard in physics. And that's for various good reasons, actually. It's not that they're lazy. It's that, the needs are different. Traditionally you would do a calculation or something that you thought could be tested by an experiment. So that's the primary thing. It's not to prove a theorem with the maximum possible generality. It's to prove the one that applies to your particular observation that you're going to measure. And so that's a different motivation, which motivates different types of proof. Again, physicists definitely want to prove things, just not necessarily using rigorous foundations in mathematics. And so that's one argument. And then, as many of you know, again, I won't talk about quantum field theory really in any detail at all, but it's famously a subject which the theories that describe our world have never been rigorously proven to exist, or even, people are looking, there's a group of mathematicians working hard on that, but it's an outstanding, there's this, for example, Clay Millennium Prize problem to show that the Yang-Mills theory, which is the foundations of the standard model and quantum chromodynamics, is a sensible mathematical object. And so that's considered an outstanding challenge that people do not know how to push through, though they make progress. So what can we do? And that's, I think, for physicists, kind of a deep question. But of course, the answer that we're going to adopt and that one can take now is that there is mathematical physics. There is a sizable part of theoretical physics which has been made rigorous by mathematical physicists. And so why don't we formalize something in that area? And that does include projects in quantum field theory. It may not include the four-dimensional Yang-Mills theory, but it does include the two-dimensional Yang-Mills theory. It includes other interesting theories that, of real physical interest. And so let's try to do that to see, is that possible? And even that is going to be very challenging because MathLib, of course, is just scratching the surface of all the depth of non-proved rigorous mathematics. But in the last couple of years, measure theory and probability theory have been pretty well developed, at least the foundational parts of them in MathLib. And so that's very valuable because one of the standard approaches to defining quantum field theory is to turn it into a problem of defining a probability measure satisfying certain axioms. And there are others. So for example, you can regard quantum field theory as a example of quantum mechanics, which it certainly is. And then there is something called the Whiteman axioms. But the prerequisites for quantum mechanics in MathLib are much, much weaker than the prerequisites for a probability theory. I mean, there is Hilbert space, but there's, like, for example, there's hardly any PDE, not to mention, the things that you would need for quantum field theory. So that would have been a very hard way to go. But in this probabilistic framework, which is usually called Euclidean quantum field theory, there's something called the Osterwalder-Schroeder axioms, which are directly conditions on a probability measure or on expectation values within the probability measure. And so that's what we're formalizing and then trying to prove them for a simple example, which is basically a particular Gaussian random field, which is the Gaussian free field. So it is certainly an example. It's not the most interesting example for a physicist, but it certainly is a very fundamental and basic example. And it's important in this business to have examples of the axioms that you formalize and to make some distance formalizing them, because it's all too easy to write down and formalize what you thought were the axioms, but then they turn out really not to be correct, or perhaps they're correct, but you can't actually do anything with them because of some choice you made. And that happened to us several times in this project. So for sure, if we had just written out a set of axioms and said, here you go, that would have not been a satisfactory response to this challenge. And so we are proving them for the Gaussian free field. And we got most of the way. We didn't finish, but we got a lot of the way. So, okay, so what are these axioms? Well, basically, we have a field. Okay, so the basic concept, which I'm not spelling out carefully here, we'll see it in the formalized documents, is that there's space-time, which for us is R4, and it's just our Euclidean R4 with the standard positive definite metric. We have a metric, and then there's, of course, functions on R4, and you might say a field is a function on R4, and from some very intuitive physicsy level, that would be an okay definition, but it's really not a math definition because you need to say which functions. And then it turns out that the probability measure, but let me come back to that, because what is the probability measure? It's basically giving me a Gaussian. I should have written it out here. It's a Gaussian whose weight in the exponential is involved the partial derivative of the field phi squared plus something plus phi squared. Okay, so it's a quadratic functional of the field involving two derivatives. It's basically the energy functional that would give you like a a Laplace type of equation. And so that's hidden in this measure d mu, because if you start thinking about what functions does that measure have support on, in fact, you find that it's not continuous functions. It's not even clearly functions. And in fact, this topic has been, goes back to the 60s and 70s and has been updated. And so the framework that we're going to talk about, the field, well, the field is a space of distributions. Okay, and so to define a distribution, you need to define a space of test functions. And so then this phi of f is the pairing between distributions and test functions. And f is going to be for us the space of a Schwartz Schwartz test functions that decrease faster than any power at infinity, and their derivatives decrease faster than any power at infinity. And then phi are the distributions, which are the weak dual space to that space of functions, the Schwartz distributions. And so mu is a measure supported on these phi's, and then the basic quantity that we're trying to characterize, we could characterize mu, or we can characterize the generating function of correlation functions, which is what you would call the characteristic function also in probability theory, this functional of the function f given the pairing and given this measure on the distributions phi. And then that's just a probability measure, and most probability measures do not correspond to quantum field theories, and that these axioms tell us a subset which do correspond. And there's variations on these axioms. Some of them are obvious to both physicists and mathematicians. So Euclidean space, of course, has an isometry group, Euclidean group, and clearly the measure should be invariant by what I told you. Certainly the Laplace equation was. And so this functional should be invariant. That's axiom OS2. So that one's pretty straightforward. And then there are some technical axioms, such as we're going to extend this to take values for complex functions, and then we're going to insist that this function was analytic. And again, if you just naively think of this as the non-existent Lebesgue measure on the space of distributions times the Gaussian, then you would say, yeah, that makes sense. The Gaussian makes everything decay much more rapidly at infinity than this. So everything should be analytic. All these integrals converge. So that's a valid thing. That's in fact stronger than what you need, but that was what Glim and Jaffe used, and we'll use that in our project. There's another regularity axiom about the growth of this functional with complex test functions, which we're going to use. Again, it's kind of obvious for us for the Gaussian. We're just going to be able to use L2 here. And then there's a kind of a non-trivial axiom that is called reflection positivity. And let me see if I explain it. I don't think I explain it in the detail that it deserves. So reflection positivity is basically to say you have a test function which is supported. You cut space into two parts. You imagine one direction is time, and then there's positive time and negative time. And that A is supposed to be a test function only supported in positive time. And theta is its reflection, just exactly, t goes to minus t, now supported at negative time. And then any expectation value of the product of these things should be non-negative. And then that's a kind of a funny condition from the point of view of probability theory, but that's a very crucial one that says that now there's a way of taking this probability measure and turning it into deriving a Hilbert space, a measure not on all of space-time, not on 4 dimensions in the case of the Euclidean 4 dimensions, but on a spatial plane, say 3 dimensions, for RD reduced to D minus 1, and there's some Hilbert space of functions, functional on functions on RD minus 1, and that has to be a Hilbert space with a positive definite inner product, and that's a axiom of quantum mechanics. So in some sense, this is the most interesting of the axioms, and one has to prove it. And there's the ergodicity, which I won't actually get into, but that you can in the case of hand, we can simplify that to basically a decay condition on these correlate functions, what's called cluster decomposition. Okay, so here's, and I'll put up again a demonstration with some of these things in more details, but we defined the generating functional. I'll show you, and then here's the way axioms like this look in Lean. Okay, so they analyze the axiom. We have a finite set of complex test functions, and then we substitute those into this generating function of the correlation functions, and it's entire in all these variables z. So that's how you would say something like this. Regularity, this is kind of copying the expression I had on the slide. Euclidean invariance, we have a general, so for all G, which live in this Euclidean group, and all test functions, the generating functional is invariant under the Euclidean action of this G. That's very straightforward. The reflection positivity turns out to be a little bit more complicated to state than what I had on the slide back there, but this is a valid form of it to say that we have again a finite list of these positive time test functions supported on the positive half space, and then we define a matrix of basically correlation of the function I, fi with its reflection of function fj, and then this should be a positive semi-definite matrix. And so that's an axiom that we should, and so now the goal is going to be show that there's some probability measure which we will derive from a Gaussian. And in fact, a simplifying thing here is, of course, that if you had a finite dimensional Gaussian for mu here, then the generating the characteristic function would also be a Gaussian. You can just do that integral, and you'll find that that's a Gaussian. So that's a great simplification, and we'll rely on that. In fact, what we're going to do is we're going to postulate this generating functional as a Gaussian, and then we're going to appeal to another theorem to argue that yes, there exists a measure, which is a probability measure, such that we reproduce the integral over that measure. Its characteristic function is the postulated characteristic function. So that's how we in this project are going to construct this measure. There are other approaches one could take. And again, if you can go on, if free field is not going to get the physicists excited, but this the known results, if you kind of superpose them into various dimensions that people have accomplished, you could actually imagine defining theories that are relevant for mirror symmetry, the 2-2 gauge linear sigma model, and then imagine getting the physics argument for mirror symmetry, which is much simpler than the math argument for mirror symmetry, into this language and some sort of formal proof. Okay, so I'm about to put up the demonstration, and we'll see some details of that. And the other comment that I'll make, which we're still working on it, but we've decided that some of the theorems that we rely on, we're not going to formalize from the foundations and from MATLAB, because there are some theorems which are pretty standard and pretty hard to prove, and we feel that that's the job of the mathematician. So if we state the theorem properly as an axiom, then we feel, we can use that to prove our physics or our, Osterwalder-Schroeder axioms. We feel we've done our job. And so that includes things like the Planck-Charel theorem, which is very standard. It's that, L2 goes over into L2, and for a transform on the real line. The Minlow's theorem, I'll talk about a bit. That's exactly this theorem that we're going to use to construct the Gaussian measure, to argue that this Gaussian measure exists from the generating function. And so we use various coding assistants and tools, and that's what I'll put up next. And in particular, I'm going to show you a Copilot that's connected to basically not everything that I know about, but something called Lean LSP, which allows the coding agents to do the lean things you can do with VS Code. And then GPT-5 Copilot and Claude Code are all integrated into that. So let me try to put that up. Are there questions? Well, see if I can make this work.
Yes, Michael, could you mention the
Yeah.
repository where these axioms appear?
I'd rather not, because we're still working
Okay.
on it.
Thank you.
I will do that once we have them in a sufficiently nice shape. I mean, you can actually probably see it on the screen, but it is not at this point a public thing. So, okay, do people see the, yeah. Let me see if I can get this thing off of high video panel. Like floating meeting controls. Okay. So this is the okay. Let's start with the basic. I mean, so as you can see, there's many files. This is not a small project, and then let's slide this over. So this is the first file. Well, there's actually a couple of things that are like things that really should have been in MathLib, like this functional analysis file. But this is the first file proper of the project, with definitions like the space-time dimension, which we've just taken to be 4. But of course, you know, at most points you could change that. Space-time vector. Space-time is the Euclidean space of that dimension. Test function is a Schwartz map on space-time, and then there's complexified test functions here. And then the main, okay, over here you see the state of the lean prover in any of these given things. And so now we have the pairing between a field configuration and a test function. A field configuration is the weak dual of the Schwartz maps. And then that allows us, and then we have to define the pairing to a complex test function, which we do by taking real and imaginary parts. And then that allows us to define the generating functional of so we have integral over the measure here, d mu. So this is again just a general definition. You give it a probability measure over field configurations. You give it as a function of test functions, and it's the integral of that e to the I phi j, pairing phi j with over the measure. Okay, so that's the primary definition that we'll rely on. And then let's get to the axioms here. So, okay, so already we've had to define a fair number of things, like the action of the Euclidean group, the discrete symmetry that includes time reflection, the positive time test function, the complex properties of the complex test functions, and so forth. And then OS0 is what I put on the slide. OS1 is pretty much what I put on the slide. There's this kind of extra condition that you need for our case. Real positivity, profession positivity for real test functions is what I put on the slide. And then this is the statement of ergodicity, but we're going to turn that into a statement involving cluster decomposition at some point. So we have not yet proven that one, but we've proven all the others up to some intermediate results, which we think are pretty obviously true, but they're taken as axioms. And so let's look at some example of that. Okay, so here's the construction of the Gaussian free field. Okay, Gaussian free field. Kind of that's good stuff there. Okay. this uses the Menlow's theorem. Okay, so the Menlow's theorem, again, we put it in as an axiom here. So yeah. Okay, so axiom, Menlow's theorem, and axiom, Menlow's uniqueness. Okay, so this is the point where you better be, pretty careful with the definitions, and we try to make like simpler examples of the things, to have confidence that we've properly stated. This is Faulkner's theorem, which is the finite dimensional analog of this, and then the Menlow's theorem that we have a measure on some nuclear locally convex space. Here are the properties that the generating function has to satisfy. It has to satisfy a positive definiteness property, has to be continuous, and so forth. And then you guarantee the existence of this measure that reproduces the characteristic functional. And then we proved that, and this was kind of a pain. This proves it for the real test function, because that's the definition of the characteristic function. But then you need to prove analytic continuation, and that's going to be some long series of things. Okay, so this is proving that the Menlow's theorem actually does reproduce the Gaussian in this file. This is going to be, let's see what we got here. Again, it's clearly a long proof that I can only show you a few ingredients of. I'll show you some examples of things that don't require quantum field theory that showed up and that were required. This is required for the OS3 axiom. We copied a proof in Gilman Jaffe's famous book. And so this is a Frobenius positivity. So you have one non-zero positive semi-definite matrix. You have a second positive definite matrix B, then basically trace GB is guaranteed to be positive. So, pretty obvious. And not obvious to Lean, not in MathLib. And then we proved it for the positive definite matrix. And then we used continuity to extend it to the positive semi-definite matrix. And so where did all this come from? And now the magical thing is that I did not write that code. I basically had the chatbots, GPT and Claude Code, write that code. And so it's really not something that you could have done back in January or February of this year. It's really very rapidly emerging, the skill, the ability of the even commercial language models to do that sort of thing. And so part of the paper will be to talk about, the various, tricks or, ways to make that, this, at least in our experience, is kind of the limit of what these things can do, but that limit is pretty high, you can see. And then of course, next year it'll be even better, and then many companies such as Math Inc. and others are working to optimize this technology to do theorem proving in mathematics. So this is going to, I think, rapidly take off this type of ability. So let's see if I don't think I'm going to try to literally do the demonstration where we ask the language model to do, manipulate the code, although it would be fun to do it. That could be another talk for some other time. But if you look at the right-hand window, this is the GPT chat window, and this was asking it to basically move, again, there's some combination of, you writing new stuff. So it often is very good to ask it to plan, here's a statement, here's, first try to write the statement in Lean of this standard math, and it knows a lot of math. And again, it may have the advantage that this is a 60-year-old problem. So there is quite a bit written about this problem, and it is rigorous math, but it does know a fair part of that. Again, it doesn't know it perfectly, and you have to watch what it's doing, but you can now do great advantage of the verification that if a theorem is actually proven, then it's proven. So, so a lot of this is try to make a statement which is exists mathematically. Of course, the definitions we had to start with, that basic Darwin, that basic definition we wrote, and again, it even changed a little bit in the start. We learned more about the problem, and then take a statement such as this Frobenius statement. Well, let's first state it. Let's state it where it's being used to make sure that it's being proven in the form that we need it. So I think it's being used in this Hadamard X file. And what this is basically the theorem, which I hadn't known, which is that, as you know, if you take an exponential in the standard sense of a positive definite matrix, that's a positive definite matrix, and that's kind of clear. But what I certainly had known is, suppose you define the exponential for each matrix element separately, or in other words, you could say there's this Hadamard product of matrices, and you use that in defining the exponential instead of the ordinary product. Well, that also preserves positive definiteness. E to the a positive definite in this Hadamard sense is also positive definite, and similarly for positive semi-definite. And so that's what this uses, and then the Frobenius result basically only gets used in here. And so we have to define the Hadamard series as a power series. We have to define, its positive definiteness, its continuity, and so forth. Again, all this code written by the language model with a certain amount of coaxing. And then at present, I use both GPT-5 Codex and Claude Code. So if I bring up, let's bring this up. Yeah, so this is Claude Code, and we can tell it to describe this file. So again, in the real work, we would tell it to, try out writing this code. Then we look at the lean definition. Does it look like a rightly statement of what we're trying to prove? And well, okay, go to work, start trying to prove it, and then it might get part of it done and get stuck. And then GPT-5 at this point is actually better in making the first initial sketch of the proof, but Claude Code is better at actually fixing bugs and stuff. And then one has other, they each have their own talents. Okay, there's the other few of the file: Hadamard entry-wise product, entry-wise exponential, Hadamard powers, mean theorems, preservation of positive definiteness. Okay, and then again, this is partly from the comments in the file, but if I ask it, are the comments consistent with what's actually defined in the file, it's good enough to know that sort of thing. And then this gets used in the OS3 proof. So, okay, I think that's kind of making the point that the technology as it exists is extremely helpful and advancing rapidly. And so let me, yeah, I think I will stop the share at this point. And see, how do I do that now that I lost the stop sharing? Okay.
Okay, well,
Yeah,
thank you very
okay,
much,
let me
Mike.
stop there. Sure, I have a conclusion slide, but it's basically going to be saying, this is what we did.
Any questions?
I'd like to
Yeah,
say
yeah.
something.
Hi.
Hi, Mike. I learned something amazing during your lecture.
Yeah.
Because the camera was on the side of your face, I saw that there's another way to put earbuds in one's ears.
Okay. Well, that's
For
valuable.
10 years, my earbuds have always fallen out and been lost, or I've had
I learned that recently too. That is a
or
valuable
adhesive tape
lesson.
holding them
That's
in,
right.
and
Okay.
my case is a gummy mess.
Right.
And I
Okay.
tried while you were talking, I put them in the way you
Exactly.
were,
They
and
curl around in
fit
the ear, and
perfectly.
they really stick in much better. Okay, so that's a
Well, I
valuable
think
lesson
we
for
share a
everybody.
deformity.
So, yeah. Okay.
Maybe we share other.
No. They're designed this way to really go into the ear properly. So are there questions about the theorem proving, the quantum field
No,
theory,
I
the
just
lean, these other
this
things?
is what I learned. Thank you.
Yeah, sure.
Other questions? Yes.
Yes.
Excuse me. Could you introduce me some literature on optimization of quantum field theory?
I'm sorry, who's asking?
It is me, Dine Kim.
Hi. Okay, I mean, so literature and axiomatization. I mean, again, this Glim Jaffe book is very classic. It's old, but it's still, as far as it gets, it's one of the best books on the topic. Now, there are many lecture notes that, depending on which approach you want to take, and there's several approaches that I think are more modern. And if once you get into the interacting theories, they're probably better. And I would say that if I were to continue on this, I would go with the rigorous stochastic quantization approach that Martin Harrer and a large group of mathematicians have been pursuing. And then there are, I think, what's his name? Let me look up a good reference on that. Yeah, Chevyrev. So if you look up Chevyrev, it's on archive. You'll find a nice kind of introduction to this approach. I mean, this is going beyond the axioms. Of course, they use the axioms. There's a nice kind of a recent physics examination and justification of the axioms by Slava Richkov and some collaborators. Let me see if I can find out for you. Maybe I'll add a slide to my talk that includes some of these references. But in terms of the axioms themselves, and okay, Kravchuk, Chow, and Richkov, this is a recent. Again, you know, I mean, the axioms actually have aspects that need work because the basic, and I believe this is still the status, is that the Osterwalder-Schroeder axioms give all the conditions if you assume that this Euclidean measure is a probability measure. But in many interesting cases, the Euclidean measure is not a probability measure. And the basic example of that is if you have like a theta term like you have in QCD, then that's e to the I theta times, you know, integral f wedge f. And so you need to extend to complex valued measures. And then I don't think there's a necessary and sufficient condition known for a complex value measure to correspond to a quantum field theory. It's clearly like what's out there, but I think that is an open problem. But anyways, this Chevyrev would probably be and the Kravchuk et al. Would be good places to start to get a sense of the modern point of view. I have a review that will be coming out soon of the Yang-Mills problem, but that'll be in the Nature Physics reviews. That will basically have more references. It obviously doesn't go into depth about the definitions. More questions?
Thank you.
Sergey, did you have a question?
Yes, Mike. My experience with Lean is from year old. Could you comment on your setup and practical things that you found useful?
Yeah. So again, a year ago, this would not have been possible.
Right.
And so this is Microsoft, you know, Visual Studio Code. This is, you can go with Copilot and the best either, you know, GPT-5 Codex, you know, works very well, or, you know, Cloud Code also works very well, and it's either with or without Copilot. And then I would say you do have to kind of spring for the pro type of accounts of like at least, you know, $20 a month, and proving these like I don't have like it's not like it costs a fortune, but it certainly has cost like, you know, hundreds, you know, $100, $200, $300 to prove the thing that I showed you.
And you do find MCP useful?
Yeah, no, there's no way we could have done the project without that. Just could hardly even start it. Again, it's at the point where if I had set up to give the talk just to do that, we could take the next step of the project and say, you know, start proving this, and it would make enough progress during the hour that you would be convinced. You need this lean LSP also. So there's this model control protocol that allows the agents to use tools, and the one for lean is called lean LSP.
And when you write the proof, do you write the scheme of the proof and let it fill in, or
Well, it
you just
depends,
go?
you know, again, I think we benefit from, well, earlier in the project, we had to do more of that, and we did give it, we had a draft, and we did give it the draft as kind of, you know, here is the basic thing. And if you had like a LaTeX textbook, you know, Gluman Jaffe is not in LaTeX. I did actually take snapshots of a few arguments like that one about the OS3 using the Hadamard X. There's like half a page of Gluman Jaffe where I actually did turn the screenshot into a LaTeX and give it that, and that was a helpful ingredient. But it's really not good enough to take that and say just turn it into the proof. It took quite a bit of coaxing and dealing. But again, the thing about giving you more detailed, you know, kind of tips is that it changes. It changed from even the beginning of the project to now, because the standard GPT-5 without Codex is not that good at coding for a variety of reasons, and the codex is much better and starts to be competitive with the Claude code, which is optimized for coding. But again, they both have slightly different strengths, and that will probably keep evolving. But yeah, you do have to give it some textual sketch of what you're doing. You can copy references, you can write your own sketches, you can expand it out. People do make more elaborate blueprints that spell out more steps. If it's one thing to have like a blueprint that you could auto-formalize where you need to give a great deal of detail. And then what I'm describing here is somewhat more interactive, where it does get a certain distance, it does improve the proof, then it gets stuck. And then, it depends on the situation, but a very common tactic would be, well, maybe in fact, it's obviously too hard an argument is one possibility, but not obvious to it, but obvious to on reflection. But the other possibility is, let's assume that helper lemma X exists. Now, can you finish the proof? And so state in lean helper lemma X, try to finish the proof. Very good. Now we can switch to proving helper lemma X. And there were most of the things here that had to be employed at some point.
I see. And you do all this before you sketch the proof yourself on
No,
paper?
no. This is all interactive, so we've been working for about 3 months, again, off and on, not 3 months solid. And then this project, the style has been very interactive where, we had the, both forward backward, from the definitions and from the axioms, and then saying, how do we prove this axiom? Well, here's the statement, and then the kind of strategy I'm saying, so interactive, where it wasn't obvious to, and so that has a danger. And I'm sure that the code we will get will not be ideal from the point of view of, say putting it in MathLib. I mean, it's not terrible code, but it's not organized in general in the way that you would hope for MathLib. I think maybe that will come, but again, as a proof, it's quite solid.
And if I may, one last small question. From your repository, would there any particular part that you would recommend just to see how you formalize any part of physics, not necessarily QFT?
Let's see. Let me think about that. I think probably the right answer is to indeed put out something which is the part of it that we can put out that is done and is ready to be looked at. So again, we're most of the way, and I'm not sure we're going to literally finish from the point of view of proving everything from the foundations. But as I said, some part of the again, some theorems I think we are completely justified in saying yes, that should be in MathLib. Someday that will be in MathLib. Some theorems I actually feel I would do it differently if there were like a version 2. So like in particular, it's kind of technically hard to prove things about Schwartz test functions and distributions because the topology is not induced by a norm, it's induced by this family of semi-norms. And so you can do it, but it's a lot of work. And then the more modern work actually doesn't use Schwartz distributions. It uses these distributions of negative regularity, which have kind of more adapted to the problem. And those are defined by a norm. So that's an example of something that one could do the work, but it would be kind of wasted work. And then there may be things where we say, at the end of the day, here's this function is integrable, or here's this bound. It's kind of obvious, somebody else maybe can finish that.
Thank you.
Mike Mulligan has a question from the
Yeah,
chat.
please.
So how close are you to being able to add interactions to the theory?
Well, okay, that's a good question. And I think we could do it in 2 dimensions for the polynomial. The P-phi 2 theory is, I mean, it's definitely quite a bit more work, but at least with again, that was kind of as far as Glim and Jaffe got without like outrageously complicated arguments, because that one is very super normalizable. You just have like these local divergences that you can solve using Wick ordering and stuff. And so that we probably could do. But then to go on to like even fermions or gauge fields in 2 dimensions, it starts to be more complicated divergences. And then I think one should just switch over to this rigorous stochastic quantization formalism, which would be a fair amount of work. I think it's beyond what we could just do as physicists. But again, maybe we'll get the mathematicians interested in doing that kind of thing at that point. Again, all this is going to become much easier. Maybe it'll be much easier in 6 months. Maybe it'll be really easy in a year. So I think that's the way to look at it. Not that we necessarily put a lot of time into taking the next step now, is to try to project and envision what was suppose this technology becomes kind of relatively easy to use, then what?
All right, thanks.
Sure.
Okay. Any other questions? If not, well, let's thank Mike again. Thank you so much for your wonderful
Thank
talk.
you. Sure. Bye-bye. Anybody want to discuss more or?